All right, how's it going, guys? So I had a Zoom last night, Sunday night, before the module 9 test. I know I said I'll post the video online, but I had some issues with that. So I'm just kind of re-recording all the problems that I did on the Zoom session, kind of doing those problems over again and uploading this video online. All right, so I'm starting with problems on the homework. So on this one right here, on number 4 on the homework, I'm told if P varies inversely as B and P is 18 over 55 when B is 22 over 21, I want to figure out what P is going to be when B is 8 over 15. So this isn't really that hard of a problem, but it can be tricky because we're dealing with a lot of fractions. So as long as you can figure out how to deal with your fractions, it's not a hard problem because we're just told that P, I'm told that P and B are inverses of each other, except the form P equals A over B. So all I need to do is plug in P and B, and then just solve for A, and I can use that A to solve my P when B is 8 over 15. So I'm told P is 18 over 15, or 18 over 55, sorry. And that equals A all over 22 over 21. And anytime we divide with fractions, I can just flip the second number or the bottom number and multiply across. So that's the same thing as 18 over 55 equals 21A all over 22. From here, I'll solve for A. I'll multiply both sides by 22 over 21. So from here, 22 and 55 are both divisible by 11. So 2 and 5 over here. These are both divisible by 3. So I get 7 and 3. Or, sorry, 7 and 6. And what I get is that my A value is going to be 12 over 35. So A is 12 over 35. So I can put that back into my original equation. So I have P equals 12 over 35. That's my A value all over B. But that's the same exact thing as just saying P equals 12 over 35B. It's the same thing. So from here, I'll plug in my B value. So I want to figure out what's P going to be when B is 8 over 15. So I'll plug that in. So I have P equals 12 over 35. Multiply with my V value is 8 over 15. So just like before, I have a fraction in the bottom. Well, a fraction of a fraction on the bottom. So I can rewrite this as 12 times 15 all over 35 times 8. Right? You can flip that fraction and put it on the top, and that's what I did. So 8 stays in the bottom, 15 goes to the top, and now I can just reduce this down. And what I do, I see 12 and 8 are both divisible by 4, so I get 3 and 2. These are both divisible by 5, so I get 3 and 7. So I end up getting 9 over 14. So I know that when B is 8 over 15, P is 9 over 14. And that's how you do this problem. Like I was saying before, it's not a particularly hard problem, but it can be very tricky because you have all those fractions in there. And if you're not very good with knowing how to cancel fractions or kind of reduce them down like I did here, it can be a pretty hard problem. All right, so let's keep on going. Next, we're going on to number 6. And on this problem, I'm told 14 construction workers can finish a bridge over a 4-lane highway in 12 weeks. How many more equally skilled workers will be required to finish a similar building or similar bridge, sorry, in 8 weeks? So I have like a few I have a few numbers going on here. I've got 14 construction workers, a 4-lane highway in 12 weeks. So I need to figure out, well, what's important and what's not. What do I actually care for and what do I not care for? I'm being asked how many more equally skilled workers will be required to finish a similar bridge in 8 weeks. It's a similar bridge, so that 4-lane highway part is kind of pointless. I don't care for it because I don't care for the relationship between anything with the highway. I care about the relationship with the workers and the amount of time it takes to finish the bridge. So I care about that relationship between the workers and the amount of time to finish the bridge. So that's what I'm going to set my inverse variation with. And also I know this is going to be an inverse variation because the variables are kind of going inverses of each other, right? The more workers I have, the less time it'll take to finish the bridge. And that's kind of how it goes. If one goes up, the other is going to go down. So in this case, I know that W will equal A over T. So I can say when 14 construction workers, I have, it'll take me 12 weeks, or in other words, my A is 168. So I can put this back in and say W equals 168 all over T. And then from there, I'm going to plug in my T of 8. I get W equals 168 divided by 8, really ugly 8, so divided by 8, and when you put that into a calculator or whatever you want, you get that W is 21. So I need a total of 21 skilled workers to finish a similar bridge in 8 weeks. So how many more do I need compared to the 14? Well, I need 7 more. And that's going to be your answer there. Let's keep going. Now going on to number 8 and number 9. So these are some table problems, and I need to figure out first if it's an inverse or direct variation, and then I'm going to write the equation that I get from it, and then once I write the equation, I'm going to solve what they want me to solve for. All right, so for part A, I'm told the speed of a bicycle in miles per hour when a cyclist pedals at various rates in revolutions per minute with a bicycle in a particular gear. What is the bicycle speed when the cyclist pedals at a rate of 72 revolutions per minute? So that's like the setup of the problem. But if I look at the table, I can see that I have some pairs of points, and I can figure out, well, am I direct or inverse? You're a direct variation if the ratios between these variables are always the same for each pair of variables, right? Or each pair of points that they give. So 30 divided by 5, that gives me 6. So R, if I do R divided by S, I get 30 divided by 5 is 6. 60 divided by 10 is also 6. 90 divided by 15 is also 6. Since it's always the same, that tells me that this is a direct variation because when I divide my variables, it's always the same thing. If I multiply them together, like if I did R times S, what I get is 30 times 5 is what, 150. 60 times 10 is 600, and they're not the same. So when you multiply them together, like R times S, and you get the same thing, that tells you it's an inverse variation. But if I divide them and find the ratios, and it's always the same like it is on this problem, that tells me that it's going to be a direct variation. So that R times S didn't work, they were different. So in this case, it's R divided by S. And also, it doesn't really matter if you do R divided by S or S divided by R. You're going to get the final answer to be the same either way. It doesn't actually matter, but what does matter is to stay consistent with what you did. When I was checking if this was a direct variation, I did R divided by S equals 6, and that's what I'm going to stay with. R divided by S equals 6. So when I solve for R, I can multiply both sides with S to get R equals S times 6. And that's what my equation is going to be. My equation is R equals S times 6. And now I'm going to figure out, well, what's my speed going to be when my R is 72? So when R is 72, I get S times 6, or I get that S equals 12. Okay, on to number 9. Number 9, I told the number of laptops sold in a month when the store sells a particular model of laptops at various prices. How many laptops will be sold in a month when the store sells the laptops for $500? So these are my relationships right here. So I'm going to figure out, well, it's a direct or inverse. I can see right away that it's not going to be direct because 60 divided by 6, or 600 divided by 60, that gives me 10. It is 720 divided by 50. I'm not sure what that is off the top of my head, but it's definitely not 10. So I know that it can't be a direct variation. So I'm going to check if it's an inverse variation. So I'll do P times L. This gives me 36,000. That also gives me 36,000. and this also gives me 36,000. So in this case, P times L was the same for each pair, so it is going to be inverse variation. And when it comes to inverses, it actually doesn't matter how you write it. If you do P times L or L times P, it doesn't matter because, you know, it's multiplication, it's the same. You multiply any order you want to, you'll get the same answer. So P times L is 36,000. And I need to figure out how many laptops will be sold in a month. The store sells laptops for 500. So I'll say L equals 36,000 divided by 2. And this right here would be my equation. And now I need to figure out, well, what's my L going to be when P is 500? So L equals 36,000 divided by 500. When you do that, you get 72. So you sell, or the store would sell 72 laptops if they're selling laptops at $500. Okay, now number 11, and the homework, solve for T in this equation. So it's just a literal equation. Anytime you have to solve for T and you have it happening in multiple different places, what you need to do is expand the whole thing out, isolate the T's, and factor it out so you only have one. So when I multiply this out, I get RT minus RV equals TB minus 2TW. I'll move the 2TW and the TB to the left side and move the RV to the right. So I want all the T's on one side by themselves. So what I get is RT plus 2TW minus TB equals a positive RV. Factor out a T on the left side to get R plus 2W minus V equals RV. And I get that T equals RV all over R plus 2W minus V. And that looks like an exponent, but just R. And there's your answer. Just expand the whole thing out, put all of the T's on one side because that's what I'm solving for. Factor out that T, then isolate it by itself. So now I'm going to go ahead and graph number 18 and list out its domain and behaviors. So first thing I'm going to do is rewrite this as negative 2x plus 14 over x minus 4. It's just a little nicer to work with when it's like that. I'd rather have the x's first. So for me, I'll divide the top with the bottom. So I have negative 2x plus 14 divided by x minus 4. X goes to negative 2x, negative 2 times, and I get negative 2x plus 8. Subtract these. Negative 2x's cancel out. 14 minus 8 is 6. So my equation here is 6 divided by x minus 4, all minus 2. So that's what my equation is going to be. So looking at this, I can tell that my vertical asymptote is at 4. And then my horizontal asymptote is at negative 2. And honestly, we could have seen that from the very beginning because that part right there, our Bobo bond ECC, that thing, exponents are the same, divide the leading coefficients. Negative 2 divided by this one right here gives you negative 2. So that's kind of an aside, but those rules we learned with complex rational functions still apply to the simple ones. So in this case, we could have solved from the very beginning that my horizontal asymptote would have been negative 2, and my vertical asymptote would have been 4. But it's not a big deal. We got the equation. And now what I'm going to do is, when I'm looking at this green one right here on the side, I want to graph this function. So anytime you don't have a b value and all you have is an a value, I can take factors of the a to be able to graph my function. So in this case, I don't have a b value. So that means that I can take the 6 and list out both the positive and negative factors of 6. So I can say, well, I have 1 and 6, 2 and 3, 3 and 2, 6 and 1. That's the positive side, and that will give me one of my branches. And then I can also say, well, negative 1, negative 6 gives me 6. Negative 2, negative 3 also gives me 6. Negative 3, negative 2, negative 6, negative 1. These are all the factors that give me 6. So what I can do is I can go to the intersection of my two asymptotes. And I can treat that like it's a completely new origin, kind of, right? So I can treat that intersection of the two asymptotes as a new origin, and all these factors, they're just basically just ordered pairs starting at that intersection of asymptotes. So I have 1, 6, so I can go right 1, then up 6, right here, and then also positive 2, 3. So I'll take it right there, right 2, up. All I need to really graph 2, and that's what my graph will look like more or less. And then I'll do the from the negative side now. So I'll do like -1, -6 as well. -1, -6, then -2, -3, and same thing. So that's what my graph will look like. Now it's my end behaviors. As x goes to infinity, my f of x will go to -2. X goes to -infinity, f of x goes the same way. And I can know that right away because your end behaviors of any graph will always go towards the horizontal asymptote. If you have a horizontal asymptote, your end behavior is that it's going to those horizontal asymptotes. And that's why I know for both of these, it's going to be -2, and we can see on the graph that's exactly what it is. And then for the asymptotic behaviors, that's the behavior of the function as it goes around the asymptote. So as x goes to 4 from the right side, look at the graph, it's going up to positive infinity. And as x goes to 4 from the left side, it's going to negative infinity. And that's the problem. Oh, and me domain. Let's do domain. My domain is always going to be it's going to be everything except for my vertical asymptote or my discontinuities. So -infinity to +4, union 4 to infinity. That's my domain. And then for my range, it'll be very similar. It's everything except for what y cannot equal, and y cannot equal -2. So that's what we're going to write. There's your domain and range as well. All right, let's keep going. So number 22 is the same thing. We're going to graph it. Go a little quicker this time, but what's special about this problem is that we're going to, what's it called? We're going to have to actually solve for y. So it's a literal equation. I need to solve it out. So first thing I'm going to do is multiply x plus 3 and y minus 5, and I get xy minus 5x plus 3y minus 15 equals 4y minus 24. So I want to add like terms and put all the y's on one side. So that 4y, I'm going to take it, move it to the left side, and then this 5x and -15, I'm going to move it to the right side. So when you do that, what I end up getting is xy minus the 4y over gives you -y, and that will equal plus 5x, so 5x minus 9. Factor out the y from the left side to get x minus 1 equals 5x minus 9, and I get that y equals 5x minus 9 divided by x minus 1. So then from here, I'm going to divide the top with the bottom. So 5x minus 9, I'll put it right here, 5x minus 9 divided by x minus 1. We go into it 5 times. 5x minus 5, subtract these. -9 minus -5 is the same as -9 plus +5. That gives me -4. So when I'm going to write my new equation, it'll be y equals this remainder over my divisor plus my quotient of 5. So this right here is what I'm graphing. So I'm going to graph it really quickly. So I have a vertical asymptote at y, or sorry, x equals 1 right here. A horizontal asymptote at y equals 5 right here. And I have an A value of -4. So some ordered pairs of that, you have like -1 and 4, -2, 2, -4, 1. And then you can also say 1, -4, 2, -2, 4, -1. These are all different ordered pairs of -4. They're not ordered pairs, it's all different factors that multiply to give you -4, and they become ordered pairs starting at the intersection of my two asymptotes. So I can have 2, -2, so 2 right, 2 down, right here, and then 1, -4, so it'll be right here. So a rough sketch of the graph would be something like that. And then I also have like -1, 4, so -1 of 4 will be right here, and -2, so -2 positive 2 will be right here, and I get something like that. So I know this goes that. Like that. End behavior, domain, range, and asymptotic behaviors. I'll leave that to you guys. The answer to those are on Canvas anyway under notes, but I'll go ahead and not let this video be too long. So we're going to keep going from here. So you just figure out the asymptotes, asymptotic behavior, end behavior, domain, and range. So now I have a complex rational function that we're going to go ahead and graph. So I'm going to graph this as p of x equals x cubed minus 3x squared minus 4x plus 12 all over x squared minus 3x minus 4. So first thing I always want to do is factor out the top and bottom and see if I have any holes. So the top I can factor by grouping. So I can group these together. The left side has a common denominator, or sorry, common factor of x squared. So I have x squared times x minus 3. So if I factor it out, x cubed minus 3x squared, that's one group, plus -4x plus 12. That's the other one, all over x squared minus 3x minus 4. That factors out to x minus 4x plus 1. And then for the top, I have a common factor of x squared for the left side, so you're left with x minus 3, and a -4 on the right one to give me x minus 3 as well. All over the same denominator of x minus 4, x plus 1, and that will give me x squared minus 4 on the top, and x minus 3 over x minus 4, x plus 1. Then x squared minus 4 will factor out to x minus 2, x plus 2. So I get x minus 2, x plus 2 times x minus 3 all over x minus 4, x plus 1. So from here, I don't have any holes, nothing cancels out. So I'm going to go on to asymptotes. So that's how it goes. You factor out the polynomial and figure out any holes, look for your asymptotes, look for your intercepts. So from here, my vertical asymptotes here will be 4 and -1 from the bottom. And I need to figure out, well, how am I going to react around those asymptotes? And since they're both raised to a power of 1, for both of these, they're going to go, or the behavior is that they're going opposite ways. After that, I need to figure out, well, how about my horizontal asymptote? Horizontal asymptote, I need to look at the degrees of the top and bottom. That's your blah, blah, and ECC. And I can see if I compare the top degree with the bottom one. I have a degree of 3 on the top, a degree of 2 on the bottom, so it's bigger on top. So if it's bigger on top, that means I don't have a horizontal asymptote. Instead, I have a slant asymptote, or an oblique, or whatever you want to call it. Right, so to do that, I'm going to divide the top by the bottom. Just go down here again. I have x cubed minus 3x squared minus 4x plus 12. We're dividing that with x squared minus 3x minus 4. And this is how you're going to figure out what your slant asymptote is going to be. Divide the top by the bottom, and whatever your quotient is, that's your slant asymptote. I don't care for the remainder. I only care for the whatever it's called, the quotient. So x squared goes to x cubed, x times, multiply that out, x cubed minus 3x squared minus 4x. Subtract these. These all cancel out, and I'm just left with a positive 12. So an x squared does not go into positive 12, so I don't have any constant term here. So x just ends up being my only part of my quotient. So I know that my horizontal asymptote or my slant asymptote is just y plus x. So I have my asymptotes. So I'm going to go ahead and graph these really quickly. I have -1 right here. And +4, I'll put it right here. And I have a slant asymptote of y plus x. So something like that. All right. And now I'm going to look for my intercepts, x and y intercepts. So x intercepts are pretty easy. All you do is each of your factors on the top set equal to 0. Those are your x intercepts. So I end up having 2, 0, -2, 0, and 3, 0. Those are my x intercepts. And they're all raised to a power of 1. So that means that for all of them, I'm going to go straight through the asymptotes. Remember, if the degree of your factor is raised to a power of 1, you go straight through it. If it's raised to an even degree, you bounce off the point or your tangent to that x-intercept, that point. And if it's any odd number bigger than 1, so like 3, 5, 7, or 9, you have kind of the concave change. And now for my y-intercept, plug in 0 for x. So when you do that, p of 0, I get just 12 over -4. Because when you plug it into your original formula, when you plug in 0 for x, all these x's just cancel out. I'm left with 12 divided by -4 or -3. So I have all my intercepts now. I have 2, 0, which will be about right here, we'll say. 3, 0, right about here. -2, 0, right over here. And a y-intercept is 0, -3. So I'll put it about right here. So once you have all your intercepts, I'm going to graph it, and usually you want to start on the part where you have your y-intercept. So on this part here, I'm going to start in the middle part because that's what my y-intercept is. Let's go ahead and label it 0, -3. That's 2, 0, 3, 0. And -2, 0. And remember, for all these x-intercepts, I go straight through them. I'm not going to bounce off them. So if I look at the middle part where my y-intercept's at, I can tell that, well, I'm really just going to go through this point and kind of go like this. I don't have any other way to go about it without making new x-intercepts. So this is really the only way we can draw this graph without making any new x-intercepts. And then at x equals 4, we said we're going to go in opposite ways. So if the left side of x equals 4 is going down, the top part has to go up. That's why I know that I have a part of my graph will be up there. And then for x equals -1, that's also opposite directions. So on the right side of -1, I'm going down. The left side I have to go up, which is good because I have to go through this x-intercept. And that's what I get. And then from here, my domain will be everything except my discontinuities. So it's -infinity to -1, union -1 to 4, union 4 to infinity. And that's what you get. Let's go on to number 33. This one, I'm going to go over this one a little more quickly so we can get this video kind of over with and not let it be too long. So first thing we're going to do is always going to factor it out, but it is factored out for me, so that's convenient. After that, what I want to do is I want to cancel out any common factors. So if I look at this right here, I can see that an r plus 6 cancels out from top and bottom. And since it completely canceled out from the bottom, that tells me I have a hole at -6. You only get a hole if the factor you cancel out completely cancels out from the bottom. If it doesn't completely cancel out from the bottom, it's not going to be a hole. It's going to be an asymptote. So I have a hole at -6. And my original was the only one I'm not missing anything else. It is more fun. All right. So I have a whole at -6. So when I rewrite my fraction or my polynomial, I mean -28, r plus 1, r minus 3 cubed, r plus 4 to the 4th power, all over 45, r plus 2 cubed, r plus 7 squared, r plus 5, and r plus 3. All right, that's what I get. And what you want to do is you want to plug in -6 for r. And when you do, I'm not going to work that whole thing out. It's going to be way too long. But you plug in -6 for r. And I'll set it up with you guys. But what you should end up getting is that you get a whole at 33 at -63. All right, so you plug it in, you -6, you -28. Your -6 plus 1 is -5. -6 minus 3 is -9 cubed. -6 plus 4 is -2 to the 4th power, all over 45. -6 plus 2 is -4 cubed. -6 plus 1 is +1 squared. -6 plus 1 is -1. -6 plus 3 is -3 all squared. So that's what you get. And actually, this isn't the worst because you can reduce this down. So let's actually just go ahead and do it. So this 1 squared is useless. I'll get rid of it. -3 squared, that just becomes a 9. And then from here, this 9 and this -9 squared. Well, this -1 and this 1 cancel out anyway. So 9, you can get rid of this 9 and change this 3 into a 2. -5 and a 45. I can cancel out this -5 with this 45 and be left with a -1 and a 9 on the bottom. This 9 and this other one cancel out, so I'm just left with a +9 there. This negative and this 28 can be positive. I have this -2 to the 4th power. I can rewrite this as 4 to the 3rd. Right, this -2 times -2 gives you +4. Sorry, 4 squared. You get 4 squared there. And then this 4 squared and this -4 cubed can cancel out, be left with -4 to the 1st power. And then from there, -4 and +27, I can cancel that out. -1, 28 becomes 7. So what I end up getting is a bunch of mess, but you just cancel stuff out. You're left with 7 and a +9 on the top, so I get 63 with a -1 on the bottom, so -63. So I know it kind of looks like a mess, but you can use a calculator, expand it out a little bit more. But all I did was plug in my -6, and I saw I have a lot of things I can cancel out without multiplying everything out together to get my answer. So that's kind of how I do it. You could just plug it all into your blue calculator if you want to. I wouldn't suggest doing that because it can get really big and ugly. But you could, and you'd still get -63. So my whole is at -6, -63. I have a vertical asymptote, or vertical asymptotes at -2, -7, -5, and -3. And that's because I set each factor in the denominator equals 0. And these are the factors I get. And now you can figure out the behavior at all these asymptotes. So x equals -2 adds an odd degree, so it's opposite. At -7, it's even. We go the same way. At x equals -5, it's raised to the 1st power, so it's opposite ways. At r plus 3 squared, or x equals -3, it's an even degree. We're going the same way. All right. So after that, I want to figure out what's my horizontal asymptote going to be. So the degree at the top is it's 8 after we cancel stuff out. On the bottom, it's also 8. So that means my exponents are the same on top and bottom, so I divide the leading coefficients. and I get negative 28 over 45, which is, a little less than negative 1/2. A little more, sorry, than negative 1/2. All right. So I'm going to go ahead and graph all my asymptotes now in my hole. So if x equals negative 7, I'll put that way over here. X equals negative 5, I'll put it right here. Then negative 3, negative 2. So right here, negative 3, and negative 2 right here. And I'm going to label what happens at each of these points. So negative 7 is the same, so I'll put an S for same. Negative 5 is opposite. OP for opposite. Negative 3 the same way, and negative 2 we're going opposite direction. All right, so that's what I have. Now you figure out my x-intercepts. X-intercepts, what you do is you put each factor at the top equal to 0. So what I get is negative 1, 0, 3, 0, and negative 4, 0. And I want to figure out, well, what's my behavior at each of these x-intercepts? At negative 1, it's raised to the power of 1. I go straight through it. At 3, 0, it's a power of 3. I'm going to have a concavity change around that. At negative 4, it's a power of 4. So I'm going to be tangent to it, or you can say you kind of bounce off that point. So I'm going to go ahead and plot these points. Negative 1, 0 will be right here. It's negative 1, 0. And I'm going to go straight through that point. 3, 0, we'll put it right here. In this case, I'm going to be tangent to it, or I'm going to bounce. Oh, sorry, this is the wrong one. Concavity change here. And then negative 4, 0, which will be right here. This is the one I'm going to bounce off of. Negative 4, 0. This one will be tangent to it. I'm going to bounce off it. All right, now I need to figure out my y-intercept. Y-intercept, you plug in 0 for x, or in this case, t. And I'm not going to do this on the board, but it gets pretty ugly, but you get 128 over 525. So you plug in 0 for r, we get 0, 128 over 525. It's pretty ugly, just use your calculator for that. And that one's going to end up being, we'll put it right here, 0, 128 over 525. So you always want to start on the part of the graph that has your y-intercept. So in this case, I'm going to start at the far right, and I'll figure out, well, how can I draw this in a way that I hit all my points without making any moves? So and the only way I can see I can do that is if I start from the bottom here, I go straight through this point, I hit my y-intercept, I have a concavity change kind of like that, and I kind of just go down forever. Well, I don't go down forever because I completely forgot about the horizontal asymptote. Don't do that. So horizontal asymptote at negative 28.5. Let's go ahead and put it right here. Okay, so please don't forget about the horizontal asymptote like I did. That's y equals negative 28 over 45. So it doesn't go down forever, because that wouldn't make any sense, because we have a horizontal asymptote. So it's going to go down like that. Kind of curve into that 3, 0, and it goes down to your horizontal asymptote. And then from there, I'm going to start looking at my asymptotic behaviors. At negative 2, they go in opposite ways. So I know that I'm going to start from the top right here and go up. And then at negative 3, you go the same way. So I know I start up, I bounce off at negative 4 and go up as well. And then at negative 5, I go opposite way. So I should go down this way. And at negative 7, it should be the same way. So I go something like that. And that's what number 33 should look like. And that's what you get. Domain, it's negative infinity to each of your discontinuities in order. And I completely forgot the whole too. Sorry, guys. It's negative 6, negative 63. So negative 6, negative 63. We'll put it about right here, we'll say. That's a whole. Sorry about that. And that's what you get. So this becomes negative 6, negative 63. Don't forget about the whole, but that's what it does. The whole is just going to be like a regular point on the graph, except it's empty. You cannot equal it. And that's what you get. So don't do what I did. Don't forget about the horizontal asymptote. Don't forget about the whole. And just work with it like that. Then ask my domain will be negative infinity to negative 7. Then negative 7 to my next discontinuity at negative 6. Then from negative 6 to negative 5. Negative 5 to my next discontinuity at negative 3. Then union negative 3 to negative 2. Union negative 2 to infinity. There you go. So that's how you do it. Don't forget about discontinuities. Don't forget about your horizontal asymptote or your hole like I did. Please don't do that. So that's how you do that problem. All right, let's keep going. This one is on your Module 9 review. And I'm not going to do the whole thing with you guys because we just kind of did 2 problems just like it. But there's something I want to touch on here. And that's kind of the concept of holes and what happens when you cancel stuff out. So on this problem right here, I can see that x plus 2, they cancel out from top and bottom. And this x plus 4, it cancels out completely from the top. And I still have 1 left over on the bottom. And at the same time, at x minus 2, it cancels out completely from the bottom, but not completely from the top. But the only places we'll have a hole here will be at x equals 2 from this one, right, this factor right here, and x equals negative 2 from this factor here. Even though we canceled out an x plus 4 from the top and the bottom, I still have an x plus 4 on the bottom. If you still have a factor that you canceled out on the bottom, it's not going to be a hole. It's going to be a vertical asymptote. I still have asymptotes left over there, so an asymptote will take precedence over a hole. So if I have a hole at negative 4, but also have an asymptote there, it's not going to make much sense because there's different types of discontinuities. Or in other words, the asymptote takes precedence over the hole. So that's why at x equals negative 4, I don't have a hole because I still have that factor of x plus 4 there on the bottom that's preventing me from having the hole. It's making it an asymptote. At the same time, I still do have a hole at x minus 2, even though I still have factors at the top because it's still going to be a hole, right? I don't have an asymptote there. All it means, if you still have factors on the top, even though you cancel it out from top and bottom with that factor of x minus 2, that just means that I have a hole, at an x-intercept. That's all it means, and that's okay. You can have a hole at an x-intercept. It just means you're not intersecting the graph there, but you have a hole at that x-intercept. And that's what it means. So I can still have a hole at an x value 2, even though I still have 2 factors on the top, but I don't have any, I canceled out from the bottom. So my holes here would be at 2, 0. I get that from plugging in x equals 2 into the formula, and then at negative 2 as well. You plug in negative 2, I don't remember exactly what it is off the top of my head, but plugging negative 2 into the formula. And let me just see what the key says. You plug it in, and when you do, you get negative 2, negative 16. So that 2, 0 tells me I have a hole at an x-intercept, and that's okay. That just means you put an empty circle at that x-intercept, and that happens. That's fine. It just means you didn't completely cancel off from the top. All right. I'm not going to finish the rest. You finish the rest on your own. The work.key is on Canvas already, so you should be fine. But I did want to do this one. This is number 45 in the extended practice, and this is kind of like we had in the quiz. I give you guys an equation, 12 over x minus 8 minus 5, and I'm applying transformations onto it. So I have a factor of 1/4, or I'm horizontally compressing it by a factor of 1/4. So if you're horizontally compressing it by a factor of 1/4, that means b is 1/4. So when I plug it into the equation, I get y equals 12 over, put it down like this, y equals 12 all over 4x minus 8 minus 5. You plug in the reciprocal because inside of it, it's 1 over 2. I factor out that 4. Then I get x minus 2, all minus 5. And then 12 divided by 4 reduces down to 3 over x minus 2 minus 5. So that's what I get when I horizontally compress it. Now I'm going to reflect it over the x-axis. So I'll continue this up over here. I reflect it over the x-axis, so that tells me I have an a value negative 1. So you multiply your a and k by negative 1 to get negative 3 over x minus 2 plus 5. And then 3 units to the left means I'm going to take my h value 2 and subtract 3 from it. So h equals 2, subtract 3, h equals -1. You plug that back into x minus h, and you get x plus 1 plus 5. Or in other words, you can kind of think they do the opposite thing. We're going 3 to the left. Well, we should be subtracting it, but instead we'll add to it because everything horizontal is going to act a little weird. But anyway, that's the answer for this one. So I know I didn't go through the whole, I'm not posting the whole Zoom tutorial like I wanted to, just there's a few things that kind of went wrong with it. Sorry about that. So I recorded this video instead. Going over the problems that I thought were going to be pretty useful for the test that is tomorrow. All right, anyway, guys, this video's been long enough. Hopefully it's been helpful, and good luck on the test.